Welcome to the second video of our series, A Beginner's Guide to the C Programming Language. In the last video, we saw the essential functions of the CPU and the operating system. We also considered different programming languages and how high-level languages are converted to machine code before being executed. In this session, we will study how data is stored in memory and represented using different number systems. We will understand how simple binary arithmetic operations are performed, and finally, examine how different types of data are structured and processed in memory. Please like this video, follow our channel, and enable future notifications. As seen in the earlier video, memory is used to store data, and the CPU fetches data from memory using the address and data buses. The address bus selects a memory location and the data bus transfers the data to and fro that memory location. Memory can contain machine code instructions or data. Each instruction in the instruction set of the CPU has a unique opcode. We can see here that the instruction for moving a 2-byte value from a memory address in the BX register to the accumulator has an opcode 8B07. The CPU fetches these instructions in memory from the code segment memory block in the form of 1 or 2-byte opcodes. Like instructions, data in memory is also stored as binary values. The smallest unit of data memory is a bit that can have a value of 0 or 1. A 4-bit value is called a nibble. Now note that a bit or a nibble cannot be addressed directly by the CPU. The smallest addressable unit of data in memory is a byte, which comprises of 8 bits. A word is a term used for data that is 2 bytes wide. A double word or D word is 4 bytes, whereas a quad word or a Q word is 8 bytes. The other units of memory are a kilobyte, which is 1024 bytes, a megabyte, which is 1024 kilobytes, and so on. The amount of memory a program can access depends on the width of the address bus. Typically, this is 32 bits in most computers today, which means that a computer can access 4 GB of data. Now, all data in memory is stored in binary format, and its value can be represented using different number systems. These number systems are binary, octal, decimal, and hexadecimal. Each number system has a base. This is the number of digits that are used to represent data. The name of each number system specifies its base. So the binary number system has 2 digits, 0 and 1. The octal number system has 8 digits from 0 to 7. The decimal number system has 10 digits from 0 to 9. And finally, the hexadecimal number system has 16 digits from 0 to 9 and the alphabets A to F. Now, how are numerical values represented in each of these number systems? At a generic level, a simple electronic counter that counts up has several digits, with the least significant digit at the right and the most significant digit on the left. The least significant digit has position 0. The next significant digit has a position 1, and so on. As the counter counts up from 0, the least significant digit counts from 0 to 9. After 9, the next significant digit then increments by 1, while the previous digit resets to 0 and continues to count from 0 to 9. The same operation happens when the counter increments from 99 to 100. This is precisely what is happening here. In every number system, each digit's value increments until it reaches the largest digit defined in the number system. It then resets to 0 after incrementing the next significant digit. For example, the decimal number 11 is B in hexadecimal, 013 in octal, and 1011 in binary. How do you convert a value from decimal to another number system? Here we are converting a decimal number to binary. To do that, you keep dividing the number by the base, storing the remainder until the resultant quotient is less than the base. In this case, the base is 2. You can then assemble the result by reversing the list of remainders to get the final value. Next, we can see the process of converting a value in one number system to a decimal value. In this case, you multiply the digit with the base raised to the power of the digit's position number. The digit's position number starts with 0 in the least significant digit and counts up to the most significant digit. Again, in this case, the base is 2 because we are using the binary number system. To get the final decimal value, we then sum up the values of each place in the number. The CPU can also perform simple arithmetic operations on operands. The latest CPUs can do complex floating point calculations internally. However, earlier CPUs could only perform simple integer arithmetic operations. Now let's look at how basic operations are performed in binary numbers. Just as with decimal numbers, we can add two binary numbers starting with the lowest significant digit. The result of the addition is shown with the sum and carry value in each case. In case of subtraction, the CPU adds the first operand with the negative value of the second operand. Now, to find the negative value or to negate a number from positive to negative or from negative to positive, you convert its current value to its 2's complement form. The 2's complement form is obtained by inverting the bits in the number to get the 1's complement form and then adding 1. Here is an example of a 2's complement conversion. Let's take a 4-bit binary value of the number 6. This is 0110. The 1's complement is obtained by inverting every bit in this number, so it becomes 1001. And adding 1 to it makes it 1010. This is the 2's complement of the number. Let's observe how binary subtraction operation happens. Let's take the operation 12 minus 8. This operation can also be performed as 12 plus minus 8. At first, to get the negative value of 8, we convert it to its 2's complement form. As you can see out here, the negative value of 8 is 11111000. When you perform a 1-byte addition operation, adding 12 to minus 8, you get the following value: 1 followed by 4 zeros followed by 0100. The most significant ninth bit is truncated and the lower 8 bits contains the value of the result, which is the decimal value 4. In the example above, we are looking at byte-wide operations, where the most significant bit is the bit 7, and anything to the left of the most significant bit is truncated. In a 2-byte or a word operation, the most significant bit will be the 15th bit, and bits to its left will be truncated, and so on. Now, numbers can be signed or unsigned. In signed numbers, the most significant bit is the sign bit. If it is 1, then the number is negative, otherwise, the number is positive. While it's good to know how to perform different operations on binary numbers, a handy tool you can use to check these operations is the programmer's calculator, which can be used to perform operations and check the values in different number systems. Now, a computer can be used to store various kinds of data. Data is of 3 types. Primary data is data like characters, integers, and floating point data. Derived data is a collection of primary data types like arrays and strings. And finally, structured data is data that consists of primary and derived data in a known format in memory. This is how images, documents, etc. are stored in memory. So let's start with how primary data like characters, integers are stored in memory. A character is stored as an encoded value in a single byte or a 2-byte format. Generally, characters are encoded as bytes in the ASCII format. However, there are other character encoding formats, including EBCDIC, ISO, and the 2-byte UNICODE. The table shown here shows the ASCII table. It shows the ASCII value for each character in the character set. The table has three parts. The first part is the control code section. In C, these characters are known as escape characters. We will understand more about them when we discuss the C data types. These control characters are not displayed but instead have a specific meaning. For example, a ASCII value of 13 is the carriage return character. When sent to an output device like a console or a printer, it will reset the cursor to the first column. You can read through the other control codes in this section of the ASCII table. These will have values from 0 to 31. The second part of the ASCII table is the printable character set that contains the characters and punctuation symbols in the English language. These have values from 32 to 128. The third part of the ASCII table is the extended ASCII table, which contains special characters, mathematical symbols, and box drawing characters. As you will notice, the ASCII table is very limited in terms of the characters used on a computer. For applications to have multilingual capabilities, the ASCII table is not good enough. So a 2-byte character encoding scheme was devised. This is the Unicode standard. It contains most of the character symbols used in languages worldwide, like Greek, Hindi, and Mandarin. Now, in our discussion about data and memory, we mainly considered single byte numbers. But numbers can have multi-byte widths. For example, it can be 1 byte, 2 bytes or word, 4 bytes or D word, 8 bytes or Q word. We also know that these numeric values can be signed or unsigned. In signed numbers, the most significant bit is the sign bit. If this sign bit is 1, then the number is negative. In multi-byte numbers, it is also essential to understand how it is laid out in memory. There are two formats of multi-byte number layouts, the Big-Endian format and the Little-Endian format. The most commonly used computers today use the Little-Endian format. As you can see, in the Big-Endian format, the most significant bytes occupy low memory and the least significant byte is in high memory. On the other hand, the least significant byte occupies low memory in the Little-Endian format and the most significant byte is in high memory. Here is an example of how multi-byte data is stored in memory in both the Big-Endian and the Little-Endian formats. We now conclude our discussion on data and memory. As we have seen, the CPU accesses memory as if it's a single block of memory. It accesses data using its address, which uniquely identifies the location of data in memory. Data in memory is stored as binary values. We can represent these binary values in different number systems like decimal, hexadecimal, octal, etc. We also had a look at how characters are encoded in memory and the layout of multi-byte numeric values. In the next session, we will understand the software development lifecycle and walk through the entire process from problem definition and requirement analysis to coding and testing. We will also introduce you to some of the tools used in the process. So please like and share this video and see you again soon.